At this point, let's take a look at some of the terms that we've been throwing around and get all the definitions to these things in one place, as well as understand where these terms are used. So to start out with, there's a set of terms that we use to describe individual molecules. So those would be chiral, achiral, and achiral and meso. So what we know about a chiral molecule, it's not superimposable on its mirror image. And it has no internal symmetry. An achiral molecule is superimposable on its mirror image, meaning that its mirror image is identical to it. So this is superimposable on its mirror image, and it does have internal symmetry. If a molecule is achiral and meso, because it's achiral, it's superimposable on its mirror image. Because it's achiral, it has internal symmetry. But because it's a meso compound, it has asymmetric carbons. So each of those is a term that describes an individual molecule. Then there's a set of terms that we use to describe relationships or the stereochemical relationships between molecules. That is, what type of stereoisomers are two molecules? How are they related to one another? Enantiomers. By definition, enantiomers are non-superimposable mirror images. Okay, so we've seen examples of enantiomers already. Now let's define diastereomers, because we haven't done that yet. Diastereomers, and this definition is probably the broadest and simplest you'll ever see, stereoisomers that are not enantiomers. So in other words, everything else. So diastereomers are stereoisomers that are not enantiomers. Now, if they're not enantiomers, they're not mirror images. So diastereomers are not mirror images of one another. Now we're going to look at some diastereomers and figure out how to determine those relationships between molecules a bit later in this packet. But let me give you some examples of diastereomers now. We've actually seen a bunch. So for example, trans and cis alkenes. Those are diastereomers. They're stereoisomers of one another, but they're not mirror images, so they're not enantiomers. We saw this example. In a couple of places now. So cis and trans dimethyl cyclohexanes. This one's cis, this one's trans. The atoms have a different spatial arrangement in each of the structures despite the identical connectivity between the two structures, but they're not mirror images. So these are diastereomers. And then you'll see many examples of things like this. So this pair of structures, They're not mirror images of one another, although the connectivity is the same, and clearly the spatial arrangement is not the same. So these two are diastereomers. So we'll talk more about diastereomers a bit later, but before we get there, we need to learn a particular skill that's going to help us when we're assessing relationships between molecules. It's going to make it a lot easier to be able to do that, and that's what's called the absolute configuration, or assigning the absolute configuration at an asymmetric carbon. So this is going to be a binary choice. Your result is either going to be R or S. So those are the two possibilities for what we call the absolute configuration. It's determined using a set of rules called the Kahn-Engold Prelog priority rules. Now, this is all based on atomic number. And it has only to do with nomenclature. So there's no physical significance to this at all. It's just a way that we use to differentiate, for example, two enantiomers so that we can name them as different molecules because they are different molecules. So this is a nomenclature device, but doesn't say anything about the physical properties of the molecule. Okay, so let's start out. Look at the structure over here. Let's first of all identify the fact that this carbon is an asymmetric carbon. And so what I've done is made a model of that down below. So this is CH3, here's the H going back, here's the F, also in the plane, and then the blue is the Cl. Okay, so what you do is start at the asymmetric carbon, and then you're going to look at the 4 atoms that are directly attached to the asymmetric carbon. So in this case, it's the chlorine, the hydrogen, another carbon, and a fluorine. And we're going to compare those 4 atoms based on their atomic numbers. So start by going out 1 bond in all 4 directions. From the asymmetric carbon. So that you can compare those 4 atoms. So compare atomic numbers of those 4 atoms. So we're going to assign priorities based on atomic number. The higher the atomic number, the higher the priority. So higher number means higher priority. Okay, so let's do that. So the atom with the highest atomic number that's attached to that asymmetric carbon is the chlorine. So that's priority 1. The next highest atomic number belongs to fluorine, so that would be number 2. Carbon is the 3rd, so that's number 3. And then hydrogen with an atomic number of 1 is going to be number 4. Once you get the priorities assigned, you're going to orient the molecule so that the lowest priority group is pointing away from you. Okay, now I've done that with the model in the photograph to the right. So here's our CH3, here's the Cl, here's the F. And so your picture is going to look something like this. And then let's put the priorities on there. So 1, 2, and 3. So what you're going to do at that point is start at the group with the highest priority and start drawing a curving arrow. So go to 2 and then to 3. So from 1 to 2 to 3, and then you look at the direction in which that arrow is pointing. Okay, so that is pointing in a counterclockwise direction, which is like the beginning of writing an S. So the absolute configuration for that asymmetric carbon is S. Okay, now let's do a slightly different thing. Let's draw the enantiomer of this. So I'm going to draw the enantiomer by switching two of the groups. I'm going to switch the fluorine with the methyl group. And I'm going to leave the hydrogen and the chlorine where they were. Now I have the same groups, so the priorities have not changed. But the spatial arrangement of the groups has changed. So if we then assess the absolute configuration at the asymmetric carbon in the enantiomer, starting at 1 and then drawing a curving arrow pointing to 2 and then to 3, what we see is that this is now moving in a clockwise direction, which is like the beginning of writing an R. So the configuration, the absolute configuration for the asymmetric carbon in the enantiomer is R. Okay, so S is counterclockwise. Let's add that in up here. Okay. So point being, and this is very important and it's going to be helpful later, the absolute configurations for all the asymmetric carbons in a pair of enantiomers will be opposite. So that is very important. So if you have a chiral molecule that has one asymmetric carbon, and let's say that its absolute configuration is R, then the configuration at the asymmetric carbon in the enantiomer will be S. And if you have more than one asymmetric carbon, then in the enantiomer of the structure, they're all going to be opposite. And we'll see examples of this later on. For now, let's do some more examples. Okay, so the highlighted carbon is an asymmetric carbon. And so what we would do is assess priorities. Remember, what we're going to do is move one bond out in the beginning. So we're comparing hydrogen. Let me highlight these as I talk about them. We're comparing hydrogen to nitrogen to carbon to carbon. Okay, so the nitrogen has the highest atomic number of the 4. So that's clearly number 1. And hydrogen has the lowest, so that's clearly number 4. But we have a pair of carbons and they're tied. So what we would do then is look at what's attached to each of these carbons. So attached to the bottom highlighted carbon are 3 hydrogens. Notice that you're moving away from the asymmetric carbon. You don't count the asymmetric carbon itself. And attached to the top highlighted carbon is a hydrogen and 2 other carbons. So you then compare these two sets. So we're breaking a tie. And when we break a tie, or when we try to break a tie, All it takes is one attachment to a higher atomic number element. Okay, so in the carbon up above, it's attached to carbon, but the carbon down below is only attached to hydrogen. So that makes the carbon up above a higher priority. So this is going to be 2, and this one will be 3. Okay, so putting that together, remember you want the low priority group oriented away from you. So this is the first priority is the nitrogen, then the second is this carbon up here, and the third is the carbon in the methyl group. So we're moving from 1 to 2 to 3 in a clockwise direction, which means that the configuration is R. Let's do another one. Here's our asymmetric carbon. So assigning priorities, we can say right away that bromine, which has the highest atomic number, is priority 1. Hydrogen, which has the lowest atomic number, is priority 4. Then we have a pair of carbon atoms, and so we have to break a tie. So the carbon the carbon on the bottom, rather, just like we saw previously, is attached to 3 hydrogens. The carbon on the top is attached to a carbon, that's the carbon in the methyl group at the top of the structure, but it's attached to oxygen through a double bond. So it's attached to oxygen twice. So a double bond counts as 2 attachments. A triple bond would count as 3. Okay, so what this means is that the carbon that's attached to the oxygen, because oxygen is a higher atomic number than the hydrogens that the carbon in the bottom is attached to, that has a higher priority, so that's 2. This one's 3. And so 1 for the bromine, 2 for the carbonyl carbon, 3 for the methyl group carbon. This one is also R. Okay, let's do some more. The yellow highlighted carbon is the asymmetric carbon. Directly attached to that carbon, bromine has the highest priority, followed by hydrogen. And then we have a pair of carbons, and so we have to find a way to break the tie. The carbon at the top is attached to the methyl group carbon and to oxygen twice. The carbon at the bottom of the picture is attached to 2 hydrogens and a bromine. Bromine is a higher atomic number element than oxygen. So that breaks the tie. That means that this carbon is priority 2 and this one is priority 3. So all it takes is one attachment to a higher atomic number element to break the tie. So 1, 2, 3. And this one turns out to be S. Okay, let's do another example. Okay, all the examples that I've showed you so far have had the low priority group going away. That makes it easy to make the assignment because the structure is already drawn in a way that you can easily interpret. But there are going to be two other cases that you have to be able to manage. One of them would be, what if the low priority group is coming forward? That's also pretty easy. Okay, so let's go ahead and do this one. There's a couple of ways that you could think about this. Okay, so first of all, let's go ahead and assign our priorities. The OH is going to be priority 1. The hydrogen is the lowest priority, that's number 4. And then we have a tie between two carbons. So up here, this carbon is attached to hydrogen twice and to a carbon, whereas this carbon is attached to 3 hydrogens. So the carbon that's attached to another carbon has the higher priority. So that'll be 2, and the methyl group will be 3. Okay, so what you can do, start at 1, go to 2, and then to 3. That's a counterclockwise motion or direction. But you're oriented in the wrong position relative to the molecule to be able to assess correctly. You really should be standing behind the page so that the hydrogen is pointing away from you. So although this looks like S, the configuration is actually R. And that's simply because the low priority is coming forward, or the low priority group rather, is coming forward, and so we should be viewing the molecule from the opposite side. Okay, so you could go ahead and make the assignment if the lowest priority group is coming forward, and then remember that it's actually going to be the opposite of that assignment because you're standing on the wrong side of the molecule. So it's actually going to be the opposite of what you've assigned. So you could do that, or you could just flip the molecule over as we learned in previous videos how to redraw things so that the low priority group is going back. So if we flip this over, that puts the hydrogen back. Now the ethyl group is coming forward, the OH is on the left, and the methyl group is on the right. The priorities have not changed. We're just looking at the molecule now from the correct perspective. So now it's easier to see that this has an R configuration. Okay, so the final case, what if the lowest priority group is in the plane? There's 2 ways you could do this. There's actually probably more than 2 ways, but I'm just going to show you 2 ways, and then you might come up with a different way on your own that makes more sense to you, but I would recommend one of these things. So let's say method 1. Okay, first of all, let's assign our priorities. So it's going to be bromine as number 1, the OH as number 2, methyl group is number 3, and hydrogen is number 4. So in method 1, you want to use some creativity in terms of how you look at this two-dimensional structure, and you want to imagine yourself standing relative to that structure in a position where that bond to the hydrogen, the low priority group, is pointing away from you. So method 1 involves you imagine standing so that you're looking down the bond between the asymmetric carbon and the low priority group. Okay, so redrawing this guy. What you would want to imagine is that you're standing over here and looking down the bond between the asymmetric carbon and the low priority group, which is the hydrogen. That means that you're in the plane of the paper. So we did this when we looked at meso compounds previously. So what you would see would be the methyl group pointing straight down in front of you. The OH, which is coming out of the page, now that you're on the left side of the molecule, is going to be coming to your right, and the bromine to the left. Bromine is 1, OH is 2, CH3 is 3. So that is an R configuration. So that's one thing you can do. So if you're good seeing things or imagining things in 3 dimension, then this would be the option for you. Method 2 involves doing some drawing. So in method 2, you're going to draw 2 additional structures. What you want to do is redraw your original structure so that the low priority group is going back. So the way you're going to do that is the following. First, you're going to draw the enantiomer. And you're going to draw the enantiomer by switching 2 groups. But you're going to pick the groups you want to switch so that one of them is the low priority group, and you want to put it in the back position. So in this case, we would switch the H with the bromine. So now our low priority group is back, but we have the wrong molecule. We have the enantiomer. Okay, now you could assign the enantiomer and then just take the opposite assignment, or you could switch 2 groups again. Remember when we did this previously, when we were learning how to draw enantiomers, that got us back to the original molecule. So let's call this guy original. We switch 2 groups. That gave us the enantiomer. Now we switch 2 groups again. And now let's switch the bromine and the methyl group. So what you don't want to do is switch your low priority group out of the back position. So you want to leave that one alone. That's going to give you the original back again. And so now it's easy to make the assignment. So 1, 2, 3. And we've just confirmed that this is in fact still R.